Thank you for joining us today to discuss repowering diesel buses to zero emission. My name is Naeem Faruqi. I'll be the moderator of this session. I am the chair of the CUDA Maintenance and Vehicle Technology Committee. And today we have a great topic and some innovative companies that are looking at another approach to zero emission. So first off, we'll have Gara Hay, the president of MTB Transit Solutions, to speak about their ZEV program and what they're doing in the zero emission space. Gara has been the general manager for 3 years at MTB and previously worked at Peterbilt Heavy Truck Dealership and has over 25 years of senior management experience. Next, we'll go to Mike Polka, who joins us from Mississauga Bus Group of Companies, who is the project manager specifically for zero emission vehicles, and talk about electric as well as hydrogen fuel cell buses. So it'll be an exciting conversation. Mike has a background in engineering and previously has worked at Orion and Mercedes-Benz bus divisions. And lastly, we'll have Professor Olivier Treskisis speak from the University of Toronto's Electric Vehicle Lab about electric mobility and the impacts of the transition and repowering. Professor Olivier is the chair of the University of Toronto's Electric Vehicle Lab, has various patents, and is the chair of research chair in power electronic conversion. So it's a pleasure to have everyone here today, and I'll hand it over to Gara to kick us off.
Great, thanks Naeem. And thanks very much Naeem and CUDA for putting on this webinar today. Hi everybody, thank you for coming on today. As Naeem said, Gara Hay, I'm from MTB Transit. Wanted to talk to you today about our ZEV Clean Power Initiative. Some of you may have seen some or part of this presentation before. We've got a few updates that I want to share with you. And if you haven't seen this before, I'll give you a quick overview on who MTB is and the program that we're offering. If you could advance the slide, Naeem, please. So a little bit of MTB, leading repair, refurbishment, and now repower specialists. All we do are buses, and we've been in business since the early 1970s. We have worked on over 6,000 buses in our history. So we have seen every make, every model, every issue you can imagine on a transit bus we've handled. So we have a very experienced team. We've got over 55 workers in our shop in Milton, and these are welders, mechanics, painters, certified bodymen. Our average tenure of our staff is over 10 years. So, we've got a really good experienced crew who really know how to work on buses. Excuse me. We have a great facility. It's 110,000 square feet. It's just off the 401. It's in 2 buildings. It's probably the largest non-transit bus facility, repair facility in Canada. We have 60 bays on sites. We have plenty of room to work on buses. And recently we became ISO 9001 certified. Next slide, Naeem. We saw about 2 years ago, we started to see the transit industry in the world start to transition away from fossil fuels. And we encouraged that. We were very excited about that. And we wanted to help support and promote the move away from diesel fuel. So we created Canada's first diesel to battery electric conversion process, and we called it ZEV Clean Power. And we talked to some transit operators a couple of years ago about this idea. They generally thought it was a great idea and said, go figure this out. I think, you need to put a demo bus to prove out the concept to both yourself and to our customers, and also to build our supply chain. So we had a new flyer bus in our inventory. So we said, as a first step, let's convert that diesel new flyer bus from a diesel to battery electric. And we've made some really great strides in that. We went out to the government of Canada through IRAP and received some very generous funding to help us support this demo bus, and we really made some good progress. If you want to go to the next slide, Naeem, please. So we started converting that bus over at our shop in Milton. We're about 95, 97% complete. Here's some pictures of that bus. This is our bus that's at our engineering facility in Quebec, doing the final bring up of the batteries. You can see on the top left, those are where the batteries are situated on the roof. The top right picture shows the back end open, showing where the now traction motor has been placed in place of the diesel motor. You've got the batteries and all the inverters are in the back and neatly packed away. Very similar to a new OEM bus. You have a closer photo of that in the bottom right-hand corner. So the bus, this was our first, this is again a demo bus at our facility. If you want to go to the next slide, Naeem, I just want to show you a quick video. This was just taken a while ago in Quebec, showing the bus taking its first run. So this is the converted bus that's now running on its own battery power. So a very exciting moment for us. Great, thank you. So if you saw the bus stalling, that wasn't the bus's performance. That's probably the internet, I hope so. But we're very excited. So the bus is now very close to completion. If you want to go to the next slide, Naeem. So that was the update on where we are. So to give you an overview of the program is, on the left, we're going to take the diesel components out of the diesel bus. So removing the engine, removing the transmission, radiator, steering pump, etc. We're going to take those components out and we're going to replace it with battery electric components. So there's a new traction motors. There's going to be batteries placed around the bus. On our demo bus, we placed batteries on the roof. We placed batteries in the diesel fuel tank, and we placed batteries at the back. Again, inverters. We've got the electric steering. So the bus ends up, again, coming in, emitting GHGs from the diesel combustion, leaves in about a 6-month or less time frame, emitting clean tailpipe-free emissions. Want to go to the next slide, Naeem? So this is a really environmentally powerful play. So, one of the main goals for us in this program is to help transit operators achieve the GHG reduction goals sooner. We know many of you on this call have very aggressive timelines to be GHG reduced or free, and we want to support you with that. So we think by converting some of those diesel buses that still have a lot of life left in them, we're going to help you get to your goals sooner. Again, this is repowering. It can be in conjunction with the refurbishment program. So the goal is to extend the life of the vehicle. This is recycling of a bus. So we're going to keep the existing fleets on the road longer. And this doesn't mean placing old with new. This is just reusing and giving buses a second life. Now, the benefits of zero emission buses for a new OEM bus or our used bus are the same. There's zero tailpipe emissions, and we're going to be able to operate cheaper because obviously electricity is cheaper than diesel, and your maintenance costs are going to go down. So we have those same advantages that you have on a new OEM bus. A couple of the benefits that repowering can bring is we're going to now extend the bus life by up to 50%. And we can get this bus to you quickly. We can get it in less than 6 months. And comparing it to the price of a new electric bus, it can be quite a lot cheaper than the price of buying a brand new bus. Want to go to the next slide, Naeem? So the benefits of repowering are, for medium and large size transit operators, this isn't trying to replace buying new buses. This is to, as you're procuring new buses, either electric or hydrogen on the front end, we're going to clean up the older buses. So this is helping you support that. If you're a smaller agency, this may be your first dipping your toe into the electrification side. So you may only want to have one bus on your fleet because of budgetary constraints or kind of internal knowledge or awareness. So this might be your first way into electrification. One great thing is we're going to maintain the gross vehicle weight of the bus. So the weight that we take out in the diesel components will replace kind of pound for pound with the electric batteries and the components. So we're not going to mess up with the GVW, and we're not going to change any seating layout or capacity. It's going to be the exact same. We think this is really easier on the supply chain because you're going to give us, say, your Nova or New Flyer bus that your mechanics are very familiar with, your drivers are familiar with, your riders are familiar with. We're going to give you that bus back. It's just going to have a new clean powertrain on it. So there's not going to be a need to source a bunch of new parts or a bunch of training for your mechanics on the working of that bus, or even the driver, it's going to be very similar than the old bus that you gave us, just a lot cleaner. We have a much more detailed presentation we'd love to give anybody on this call. And a lot of that presentation shows you how the capital costs for this transformation can be recovered in lower fuel and lower maintenance costs. So there's a really good ROI model that we can share with you. And also a lot of that presentation is very technically based. So we can get in depth on exactly the components that are coming out and the components that are being replaced. And there's really good funding available. And I'll talk about that in a second from Infrastructure Canada. You want to move on, Naeem, please? We knew that the government plays a big part in being able to transition from over to clean emissions on the buses. And so we went out and we met one-on-one with, you'll see Catherine McKenna back before Christmas. She gave us a half an hour. We had a great chat with her. And the goal of the meeting was to give her the ZEV story that there is options available to transit operators. And we wanted her to include repowering as part of funding available from Infrastructure Canada. And she loved the presentation. She thought it had a lot of merit. And in fact, as you can see now, they've issued their document to say that repowering is a product that can be used for funding. We then met with the Canadian Infrastructure Bank in January, gave them the same presentation on financing. Again, they really thought the program had a lot of merit. And if you're going to go out for financing from CIB, they will allow financing for repowering as Infrastructure Canada will as well. So that we thought those were two really good milestones for us to hit. Next slide, Naeem. So here's just a couple options, or just a summary. So there's funding available for infrastructure that's been approved, financing for CIB that's been approved. And if you're thinking about maybe the best way to go at this as a pilot bus, which we encourage, there's some good funding available from the Green Municipal Fund through the FCM that they'll provide funding for up to $500,000 on a pilot project that we know some transit operators are looking at. Naeem, if you want to, I think my last slide's coming up. And here's a bit of a market update, just happened the last couple of months. So Infrastructure Canada came out with their Zero Emission Transit Fund document about 2 weeks ago. And in there is a section that says retrofits of conventional fuel buses to zero emission buses are eligible for federal funding. SNC Lavalin, the global engineering company out of Montreal, they came out with a great report that endorsed transit operators to look at repowering. And really, they think repowering is a great way to hit your goals. If anybody wants a copy of that, let me know. I can send that out. And then Durham Transit, DRT, just recently put out a proposal for engineering companies to give them engineering work on their repowering project. And in part of that RFI and RFP was they want to look at repowering as part of their strategy. So we think there's some really good third-party endorsements of repowering that just in the last few months have really come out to bring this project to light. Okay, Naeem?
Perfect. Thank you so much, Kara. Now we'll have Mike Holka from Mississauga Bus Group of Companies speak.
Thank you very much, Naeem, for the introduction. And I would like to start by introducing Mississauga Bus Group of Companies and our partner, eTraction, to the audience. Mississauga Bus was founded in 2002 by Raj Mahadeo. At this time, the primary focus was on rebuilding the engines and transmissions. Now, after 18 years of business, a lot of things has been changed, and we are looking at new technologies, and the business has expanded, involved new leading edge technology and products to be offered for the transit industry. Mississauga Bus is member of a few industry organizations, including QTRIC and QTA National. Next slide, please. Our partner is eTraction. eTraction was founded in 1981 in Netherlands. eTraction is part of the Evergrande Group, and they developed this in-wheel motor axle and patterned it with the drivetrain technology. Next slide, please. There are many benefits of converting a diesel bus to electric bus, and I would like to talk here about few of these benefits. Low number in a conversion from a diesel to electric, you will have a low number of components resulting in low maintenance cost. The number of components, there are no friction in the gears and anything specific with oil change or something like that. It's just the motor in the axle, and it's an electric motor. For this one, you will need to replace only the bearing of the motors. No gears, as I said, and low friction and high efficiency of the system. Next slide, please. Some of the components that they are part of the retro motion are listed in this slide. And beside this one, I would like to highlight some others like battery packs, battery management system, power steering, an electric air compressor, electric HVAC, electronic programmable dashboard, a battery cooling module, and also traction cooling modules. Next slide, please. Next slide shows the features and benefits of the retro motion. The main benefit here is that I would like to highlight here is the direct drive efficiency, and it's up to 94% from the battery to the wheel. Of course, the efficiency varies based on a number of different factors, such as vehicle itinerary, in service, driver behavior, season of operation, and battery state of charge. Next slide, please. The structure of the Motion 2.0. The main component is the axle. There are some other subcomponents of the axle that you see them here. The control is an intelligent powertrain control unit responsible for all driveline related function. It controls the in-wheel motor and interacts with driver input, vehicle, controller, energy system, and there are smart functions enable energy efficiency and integration with other systems in the vehicles. The Connect is a specially developed PDU, which is a power distribution unit, which is managed by the traction control and is part of the safety system of the motion. It provides the connection between high voltage DC supply and the in-wheel motor, containing all necessary functions for high voltage distribution and protection of the in-wheel motor system. The Motion tool is the software designed for diagnostic and calibration of the components in the motion system. It contains fully functionality to support OEMs in integrations, support field services with diagnostic, and even enables a remote diagnostics. It is designed in compliance with all applicable standards and communicates via UDS and via 1939 CAN communication. Next slide, please. The axle is the main component and has been designed a direct replacement of the existing rear axle in the transit buses. No structural modification needed to integrate the direct drive system into existing bus structure. Next slide. The wheel assembly consists of a high torque electric motor with a permanent magnet, high power inverter associated with a smart software to control the motor, end cover with disc brakes, waterproof steel to meet IP6K 9K, and a twin tire assembly. Also, being an electric motor, the electric motor is very silent. The integrated high power drive features intelligent control motor, self-protection, diagnostic features, and communicates through CAN through the control unit. In an unfortunate event that one of the motors fail, the bus can be driven back to the shop with one motor, no towing required. Next slide, please. This slide talks about the subframe. The subframe is a high strength structure of the Motion 2.0, connecting the two motors, the subframes and the two motors together. They forms a 13-ton electric driven axle. It is suitable for low floor bus application with inside width of 822 millimeters, which is about 32.38 inches. Next slide. Diagnostic software. The diagnostic software supports all the motion components. And diagnostics software features role-based authorizations, complies with industry standards, provide remote diagnostic, calibration, provide software updates, and also can provide test procedures. Next slide, please. This slide shows the 3D model of the vehicle, where we have some layouts of the components. Next slide, please. Again, inside of engine compartment in the rear of the bus, rear row side, you will see the batteries and the air compressor over there. Right towards the back in the middle picture, you will see the inverters and converters and power distribution box. And on the right side, you will see the cooling modules on the roof and the pipings that they are connecting with the cooling modules. Next slide, please. Additional systems that they are part of the retrofit. We could replace the existing conventional AC unit with a rooftop electric AC unit with heat pump. This particular AC unit can generate heat pump up to -15 degrees Celsius. Has two independent electric compressor that operates in 2 stages. In the event of one of the compressor failure, the second compressor can function and the vehicle doesn't have to be out of service for repairs. Next slide, please. Doing a balancing between the range and the amount of batteries that we can put on the vehicle, we decided to come up with a fuel cell to power the bus as well. This one will come in the next, in the near future, in the next project, when we're going to use a combination of batteries and fuel cells to extend the range of the vehicles. Next slide. Thank you very much for your time.
Thank you, Mike, so much for that. And we look forward to hearing more about your hydrogen fuel cell bus as it comes along. Next, I'd like to invite Professor Olivier to talk about University of Toronto's Electric Vehicle Research Center.
All right, thank you to Naeem for the invitation, and thanks for CUDA for holding the webinar. So UT Electric Vehicle Research Center was launched to bring together researchers that are pushing towards electric mobility. So these are the 6 core areas that we're working on. Everything from energy management to storage, down to power modules, of course, charging onboard, offboard, even wireless charging, as well as powertrain. So we combine electrical, computer, mechanical, and aerospace engineering. Next. So I'll just give you a snapshot of a few projects that we're working on. In this case, we're very interested in thinking of electric vehicles, whether it's a bus or a passenger vehicle, as a mobile energy source. So of course we can have bidirectional power flow on board. And so we can enable things like vehicle to home, vehicle to grid, and even vehicle to vehicle if you have a blackout in one of the vehicles. So we're working on high density power electronics using things like wide bandgap semiconductors to shrink these power converters and then enable these different power modes. Next. So we're very heavily into battery systems. So we work with mechanical and chemical engineers. We build our own liquid cooled batteries. In this case, we have a very unique BMS system that does state of health monitoring. So it does that by injecting signals into the cells, and we call this electrochemical impedance spectroscopy. So it injects signals into the cell, and then it extracts the impedance. And actually, this is very helpful to determine things like the real-time available power and also the degradation of the cells. Next. Now you heard Gara talk about second life in terms of repowering. This is another twist on second life where, of course, once the batteries had degraded, let's say about 20%, then we think there's a useful second life as redeployment in stationary applications. And so the idea here is that you design the battery module from day one to be repurposed for stationary, and that can help to support the integration of renewables, of course. And in this case, because the modules could come from different vehicles, or they have different levels of degradation, we're working on algorithms to basically split the power mix between these different modules. So some of the ones that are more degraded will supply less power. And by doing that, we can extend the life overall of a second life pack. Next. So there's a lot of work going on at U of T, of course, on autonomous vehicles. And if there's no one to drive the car, there's no one to charge the car or plug it in. So we see wireless charging as an enabler of autonomous vehicles. And we have different projects on wireless charging, either underneath the vehicle or behind it, as is the case here. And we're trying to think about solutions to the misalignment problem. So the main challenge actually in wireless charging is that if you don't park perfectly and the pads are not perfectly aligned, then the efficiency drops dramatically. And so in this case, we're actually using an electromagnet system to on a linear slider to move the transmitter pad to be perfectly aligned with the receiver pad. Next. All right, so you've seen these challenges before. The main challenges towards electrification, both passenger and transit vehicles, are cost, infrastructure, and the unknown. In particular, on a short time scale, how much energy per kilometer does it take, to fulfill the routes? And on a longer time scale, the degradation of the battery is a major financial risk. So here you can see for Tesla and Nissan, very different curves in terms of the degradation. And the main theme here is that, depending on the use case, the driver behavior and the climate and so on, there's a drastically different experience for each driver in terms of degradation. And in particular, Nissan with the air-cooled batteries are degrading much faster. Next. So drilling down now into electric bus. So this is actually from data from a company called Tessium in Toronto, which I'm working with outside of U of T. And they're focusing on telematics and participating in various e-bus trials. So this is the one out of Saskatoon. So you can see the speed profile and the power profile. So it's a very wide dynamic range. And this puts a lot of strain on these lithium batteries for high acceleration and high regenerative power. And so there's really a direct trade-off between the choice of the chemistry that's deployed in these vehicles and the cost and degradation, things like energy density, power density. And so that presents a major financial risk, whether it is repowering or brand new vehicles. Next. So just to give you a sense of that risk, so here's the economy in kilowatt hours per kilometer for this transit vehicle in Saskatoon versus the outdoor temperature. So you can see, I think we have some of the coldest data in the world up to about -40. And you can see how that efficiency, dramatically changes. And of course, in the shoulder seasons where the HVAC goes down, then you have higher efficiency. And so the idea is that, to demystify this, you need to have accurate modeling of the buses to understand, and not be surprised by this change in efficiency. So on the bottom left, you can see the energy distribution for the minus 39 degrees case. And most of that energy is actually non-propulsion loads. So it's mainly HVAC. And the battery efficiency is way lower as well. And at 20 degrees, you can see, 3/4 of the energy is going towards propulsion. And next. So as I said, telematics, in particular with electric vehicles, is the key to mitigating that risk of electrification. And with accurate models and very high performance telematics on the vehicle, you can see the Tessium box here. And thanks to, I see Mike Mackis is on the call. Thanks to him for letting us into TTC to get some data. So we have an online portal at Tessium. You can map out all of these parameters. It has KPIs in terms of regen and efficiency of the vehicles. You can see here histograms of the acceleration, which of course plays into the battery efficiency. Next. So one of the major trends that we're seeing, not just in transit, but overall in the electrification sector, is this concept of a digital twin. And Accenture, for example, has named digital twinning as one of the top 5 trends of the next few years. And the idea of a digital twin is that not only do you have an accurate model of the system, but that model is refining itself. In other words, becoming more accurate through the use of telematics. So as the bus ages and all the components, are slightly changing, then the twin is following that change. And so over the course of the vehicle, you can really predict how it's going to behave in the short term and in the long term. So this is data actually below here from a coach on Vancouver Island. So you can see the elevation is clearly not what we would have in Ontario. And so the key really here is to have accurate telematics combined with modeling to really de-risk electric vehicles. Next. So you can see here on the left is measured telematics data, and you can see the state of charge dropping throughout this trip. And on the right is the simulated state of charge using a model or a digital twin that's been tuned automatically with telematics data. And you can see how the state of charge is exactly following the measured data. And then the dynamic currents are also quite well matched. Next. So the last topic here, just in a few minutes, I thought I'd bring up just another perspective on repowering, in this case, focusing on really on the low-hanging fruit. So if you think about 3 tiers of electrification towards zero emissions, you can buy new buses, you can repower, as we heard from MTB and Mississauga bus, or an even simpler option is just to electrify the climate control. And so one of our partners at U of T wanted us to quantify what could be the fuel savings and the emissions reduction if we electrify just the HVAC system in a diesel bus. Next. So the idea here, I'm just showing the conventional architecture of a diesel bus below. The idea here is just to electrify just the HVAC system and increase the battery capacity, not as much as what you would need for propulsion, but basically replacing the lead acid with lithium, and then trying to quantify this trade-off of, if you have more energy on board, how much fuel savings would you get? Because it's, eventually it becomes diminishing returns because you have more and more mass added from the battery. So again, this is keeping a traditional diesel powertrain, but just electrifying HVAC. Next. So this is just basically what a digital twin looks like. So it's an accurate model of the bus with all subsystems. And again, what makes it a twin is that it follows the real system throughout its lifetime, and that can only be enabled through onboard telematics and basically high frequency sampling and uploading into the cloud using cellular technology. Next. So we looked at 2 drive cycles. So the one is called Central Business District. The other one is a New York bus drive cycles with a lot of stop and start, and 3 different climates. So we said, okay, if we do this repower of the HVAC system in Toronto, LA, or New York, with those temperature profiles, what benefits could be gained? Because it's much simpler and cheaper than, of course, changing out the powertrain. And we also took into account the irradiance. So as you know, you know, the sun going through the windows has a big impact actually on the thermal management load, particularly in the hot and cold seasons. Next. So this shows you some of the results here. So for Toronto, LA, and New York weather, you can see the emissions reduction for the different months with different battery sizes. So the different colors represent larger and larger batteries. So of course the baseline is 0, and you get more savings in the winter and in the summer. Of course, due to the you know, high HVAC load and the high temperatures. Next. So this is all public domain here. So I've listed the link to the paper, but the final result here basically gives you the average emissions reduction versus the battery size over a yearly basis, which is really what matters. And you can see that in places like Toronto, there's a larger opportunity just because, you know, we have very cold winters with you know, lots of heating needed and lots of air conditioning in the winter. And you can see an inflection point where there's really diminishing returns. So, you know, beyond a certain battery size, you're not getting more savings because it's more weight on the bus and it requires more energy on the propulsion side. So the table shows below that it's on the order of, you know, 10% emissions reduction at a relatively low cost. And you can see the fuel reduction is, you know, around 10% in Toronto. So this is just, again, one of the suite of options towards reducing emissions on diesel buses. Not as good as repowering, but certainly much simpler and much cheaper. So this really was the final outcome, just to quantify what was that potential. All right, so I want to thank again Naeem and CUDA for holding a webinar. Looking forward to the questions. Thank you, everyone.
Yeah, so now we'll turn it over for questions. I think we have 20 minutes on the webinar. So if any of the attendees have questions, they can put it either in the chat or the question and answer portal. While we wait for those questions, I'll start it off by asking Yara and Mike, what are the top challenges that you guys are facing from an engineering standpoint on repowering these diesel or internal combustion engine vehicles?
I'll start. You know, from an engineering standpoint, you know, we were very fortunate. We've partnered with a really strong engineering company out of Montreal called IVI. They were the engineering company that Nova had brought on board to do a diesel to electric conversion for them when they started looking at their battery electric opportunities. So, and they also work with Lion Bus when they started. So we feel really confident in the partner that we picked from an engineering standpoint. And, you know, this isn't their first kick at the can. They've done diesel to battery electric before. So, you know, it's maybe taking a little longer than we had hoped, but we want to do this thing right. And we want to make sure that we've worked through any issues that may come up. And although we wish it was done sooner, we'd rather get it done right.
On our side, on the engineering side, I will say that the main challenge was to select the right batteries for the application. There are so many variety of the batteries that you have to put them in the bus, and also the capacity that you have to add it to the vehicle, which increases the weight of the vehicle, but increases the range as well. So balance those ones very well, plus the battery management system. That one was one of the challenges that we face.
Perfect. I don't see any questions right now coming from the audience, so I will ask. Okay, so we've got one question here from Heather. What is the most significant contributor to lifespan extension when repowering?
Should I
Yeah,
go ahead, Carl?
Yeah, I mean, we've proven out that by repowering, the ability to extend the life of the bus by 50%, so bringing it from a 12-year life to an 18-year life is very doable. I mean, we do that now for diesel buses. So for us to be able to extend the life on an electric bus, we feel we've proven that out. But the big benefit is the cost saving. I mean, when you see the runway, if you're going to repower at, say, year 5 and you have 12 or 13 years of cheaper fuel and cheaper maintenance by using the battery electric, I mean, the economics are terrific. The economics of covering that upfront capital cost are there, and it actually becomes cash flow positive by the time that project is done. So, it's not that this is anything new, extending the life of the bus, but just by repowering it, we think is kind of a double whammy on that.
Yeah, and if I can speak to it, from the engineering side, and Mike brought this up as well, the choice of the battery chemistry is really important. And so the main two chemistries today would be either NMC or LFP. So NMC would have higher energy density, so you can get more energy per mass budget. But then they're also, much more sensitive to temperature variation. So even though you have, potentially more kilowatt hours on board, you need to spend more energy to regulate their temperature very carefully so that they have a long life. And so, as a result, you may be, you hit diminishing returns, because if you're in Saskatoon at -40 and you have to keep those batteries, at 25 degrees C, that's a huge amount of load. So those kind of trade-offs are really important, and there are many, many techniques that can be used to extend the lifetime, even from the OEM point of view, if you think about the regen characteristics. So again, having telematics on board to understand what's happening and to visualize, what is your peak power going into the battery? And if you change your deceleration patterns or curves, then maybe you don't stress out the battery as much, especially under worst case conditions. So there are things that can be done at the design time, and there are, also just operation tricks that can be used to extend the lifetime if you have that data. If you have the telematics, you have the portal, and you have proper training to understand how to operate these vehicles.
Yeah, I would just add as well that, as vehicles in that 12 to 18-year life cycle, and they're extended as internal combustion engines, you're seeing higher cost of that propulsion system to maintain, whereas I think as you transition to an electric vehicle, you would not have the same challenges as the vehicle ages. So there is that, and North American buses, most are spec'd to a 20-year frame. So there is that potential to see these vehicles run for a longer period. Moving on to the next question, what do you plan to offer in terms of field support for the life of the retrofit? So Mike, do you want to start, and then we'll go to Gara?
Sure. As of today, we have on-site mechanics, and also we have on the mechanic on the road. So we're going to be able to maintain the same type of service that we offer right now for the diesel buses on the electrical side. We have trained technicians on the electrical vehicles, not only for the vehicles that we're going to convert, even for the new vehicles that upcoming on the market that might need to be serviced as well. So our technicians, we start training the technicians, and some of them already trained with all these vehicles, electric vehicles, and all kinds of propulsions on the electrical side. And as I said, we have en route mobile technicians that they can go on site and support the vehicles on the road if it's necessary.
Yeah, we're very similar, Mike, as you as well. We've created an SOP document on all of the components of our repowered bus, and we will be training any customers on the maintenance of those products in their shop. But if there's any need for support from MTB, either back at our shop or we have a crew that can come out to your facility, we will support that as needed.
Yeah, I think there's a second part to that question around supply chain and how long do you intend to offer aftermarket parts. So you guys are using, I think, Mike, you're using e-traction. Gara, you're using.
Yes.
So what kind of support will you have for that product, and what kind of inventory levels will you keep?
We have fully support. We are partners with Interaction, so we have full support for the components that we are using for the conversion, and we are planning to support unlimited on this on these conversions. Also, as I mentioned in my presentation, there are not too many components to be replaced on this system beside the brakes, which is a general maintenance. On the electrical motor, we have to change only the bearings, and from time to time you might have to change the coolant into the cooling module for the axle, and also cooling module for the batteries. But the number of maintenance items, maintenance tasks in the conversion is much less than a regular diesel bus.
Yeah, and we're the same. I mean, we're using TM4 for our traction motor and our inverters. You know, they're owned by Dana Corp. They're a global powerhouse in heavy equipment. So, and we've already ordered, you know, additional equipment into our shop on both the battery side and on the motor and inverter side to have inventory if needed. You know, the one thing we're trying to do is we're trying to remove as few components as possible. So actually in our conversion, different from Mike's, is we don't change out the axle. So the axle stays, there's a drive shaft from the traction motor to the axle. So we felt it to not, if we could not change out the axle, we felt that was a way we took. So the fewer change parts, the better on our side.
Perfect. I think there's a question specifically for Professor Olivier. What are the main factors impacting battery life cycle on the bus data, and how long is possible to extend battery life cycle when using for stationary storage?
Yeah, great question. It's unfortunately not one that I can answer just in a few minutes, but so for one, and maybe Naomi, if you could go back to that slide that shows the degradation both in from Tesla and from Nissan. So the main factors impacting battery life, mostly it's temperature. So you know, sometimes there's a misconception that batteries are operated at ambient temperature, so that if you're running at minus 40 C, then the batteries are at minus 40 C. That's not the case at all. But it's also very expensive from the energy point of view to keep it within the optimum spot. And so the OEMs have, you know, kind of done this careful dance, and we've seen that in the telematics that at lower temperature they do allow it to drop, but certainly not, you know, not in the negative territory. Another one, of course, is just charging and driving habits. So I mentioned regen braking can lead to electroplating, especially at low temperature. So it's very harsh braking is not good for the batteries. And there's been a lot of studies on you know, how to optimize charging as well. So if you can charge at low power, that's less of a thermal strain on the batteries. If you can do overnight charging, that's fine. What we find in some of these trials is just, you know, they're just charging at full power and not just in time, right? So if you have good model of the vehicle and telematics, you can tell exactly what power level you should be charging to be ready based on the, you know, particular usage pattern. Another comment is that lithium batteries tend to degrade in kind of a linear fashion, and then you hit a knee where they start to degrade very fast. And so the ideal transition point to this stationary application is right around when you start hitting that fast degradation. And that's why they say, okay, 20% drop in capacity, you should probably look else, you know, to repower, or let's say new batteries. And it's not just because it's lost 20% capacity, it's because after that it becomes very risky and the capacity can drop fast, and also the available power may not meet your drive cycle. So if you put it then into stationary use with a much more gentle use case, so the temperature is better controlled and the power, most importantly, the power drawn from it is way lower than propulsion load, then it's possible to get, you know, the order of 10 years, even after that initial life. But all of this is very much evolving, depends on the chemistry, depends on the supplier. So it's, you know, there's no one answer for this. But from a risk point of view, it's very important to understand if you have a fleet of these, you know, $1 million buses, how it's progressing and how many of them are about to hit that knee where the capacity crashes in the next few months.
Perfect. Thank you. So we have 5 minutes left now in this session. Any last questions from the audience? One question I would have for the audience is there interest for the transit systems on the call of looking at this technology? Is it being explored today?
Naeem, one thing I'll offer is anybody on the call, reach out to us at MTB and ZEV, and we have a presentation. It's about an hour. It breaks down to much more detail of what I showed earlier, and it's heavily weighed on the technical side of the conversion, and we talk about the financial payback, the ROI assessment. So we encourage anybody who's thinking about it or has some questions, just give us a contact, and we'll set up a meeting on a Zoom call.
Perfect. Well, what I'll do is I'll just put up our contact for everyone. So if people are looking for the speaker's contact information, it's over here. Thank you all for attending today's webinar. Appreciate the conversation and dialogue, and look forward to seeing these products on the road.